Meet our subject, the hyper-realistic Poor Potato Man. If you're building a narrative project, your immediate desire is probably to get this character moving, but you quickly hit a core challenge. To use him, you have to ensure his worn-out clothing, his bumpy skin texture, and his facial structure look exactly the same across entirely different scenes and camera angles. Maintaining this exact visual stability is crucial. It is how you build audience familiarity and create an immersive narrative world that people actually believe in. This presents modern creators with a difficult dilemma. You can either build this character from scratch using procedural 3D workflows, or you can rely on rapid generative AI pipelines. Ultimately, this choice forces you to make a strict trade. You are either giving up iteration speed, or you are giving up absolute structural permanence. The manual 3D procedural workflow is the path of absolute mathematical control. It requires intentional design for every single pixel. The AI generative pipeline offers a significant increase in rendering speed and scalable visual output. This diagram outlines how we will evaluate the two methods. We are going to contrast their specific inputs, the required structural controls for each, and the realistic outcomes they actually produce. While the final rendering quality of these two methods is becoming indistinguishable, the underlying labor required to get there solves entirely different production problems. Selecting the wrong pipeline for your specific goals will either drain your production time or result in a character that looks different in every shot. Let's look at the initial input for the 3D path. You start by building complex procedural node trees in software like Blender to generate the character's base material. You combine specific noise textures and map range nodes to dictate the exact color contrast and physical skin geometry of the subject. The primary outcome here is absolute mathematical certainty. The character's geometry will remain 100% consistent regardless of where you place the camera. The trade-off is a massive time investment. Every bump map, texture imperfection, and physical attribute has to be built and configured manually. This manual requirement extends to environmental factors too. You have to set up deliberate three-point lighting to evoke specific emotions, like using warm tones for joy or a strong backlight for hope. This handcrafted approach closely mirrors traditional stop-motion techniques, where every visual element is highly intentional. The procedural 3D path guarantees perfect consistency, but it demands a staggering upfront investment in technical labor before you ever hit render. Over on the AI generative path, the primary inputs are text prompts and reference images fed into models like Runway or LTX. Creators typically start with descriptive anchoring, using a standardized block of text that details the character's exact clothing and features for every generation. The immediate benefit is obvious. You can generate a Pixar-level 8K resolution render in seconds across an infinite number of environments. But there is a fatal flaw. Text conditioning alone only describes visual properties at a broad categorical level. It understands what a shirt is, but not the exact tearing of your specific shirt. This chart visualizes that failure point, known as character drift. Without tighter constraints, an AI model will organically morph your character's eye shape or vest texture between generations. Relying solely on text prompts, without advanced structural control layers, ensures your character will constantly morph into a different entity. The professional solution to character drift requires utilizing structural control layers, like IC LoRa, to strictly lock down physical attributes. By extracting a skeletal structure from a reference video, you allow the model to condition the exact motion arc and proportions of the generated clip. For dialogue scenes, you hit the next layer of complexity, achieving accurate lip sync and multimodal emotion embedding. This diagram maps the audio-to-motion process. On the right, audio features encode to map accurately to physical motion frames. Down in the generated video section, auxiliary mathematical losses, like sync loss, maintain temporal coherence, preventing uncanny facial expressions. The true trade-off of professional AI is high infrastructure complexity. You are managing local GPUs, fine-tuning models, and maintaining extensive libraries of reference imagery. Achieving true character consistency in AI requires a complex pipeline management job that rivals traditional 3D. This scorecard breaks down how to choose a pipeline based on your production constraints: the precision optimizer, the agile storyteller, or the narrative purist. We map the 3D procedural workflow to the precision optimizer, artists who require exact visual fidelity and absolute control over specific elements. We map the generative AI path to the agile storyteller. For serialized content, you accept minor structural hallucinations in exchange for massive iteration speed. The gap in final output quality is closing, making the choice purely about your workflow preference. Accurately identifying your core constraint, time versus control, is the only reliable way to select the correct toolset for your project. Finally, we address the narrative purist. For this creator, no amount of technological advancement can replace foundational visual storytelling skills. Intentional choices dictate emotional resonance regardless of the software used. Warm tones communicate joy, and diffused lighting signals nostalgia, whether rendering nodes or prompting algorithms. This connects to classic narrative world-building. The environment and atmospheric visuals do the heavy lifting for audience immersion. Camera placement, lighting strategy, and overall script weight matter far more than algorithms or placing by hand. Ultimately, choose the workflow that empowers you to tell a compelling story faster and with greater emotional impact.